The sphere you see at the top of the page we'll assume is made out of plastic, or in other words, it's an insulator. Let's draw a radial axis. Now, what's a graph of electric field versus R look like if this plastic carries a uniform charge density throughout its entire volume? In other words, if rho, the volume charge density, is a constant, what's that tell us about the nature of the electric field at points inside and outside of the sphere? So we'll put in a capital R to represent the distance to the surface. Yeah, if it's got a uniform charge density, then the electric field grows linearly from the center to the surface. E is proportional to R, and then at points outside, the electric field is proportional to 1 over r squared. Now, we know it's different if the sphere is metal or a conductor. Then, once it reaches electrostatic equilibrium, charge only resides on the surface. So if you tried to place a net charge on the sphere, that charge is going to quickly reach electrostatic equilibrium. Meaning it doesn't take much time for the charges to redistribute themselves so that they do reside exclusively on the surface. And then it guarantees the electric field is 0 inside. So the graph of electric field versus R, in this case, it's 0, and then it points outside. There's no distinction between the metal sphere and the plastic sphere. It's still proportional to 1 over r squared. This doesn't matter whether the metal is hollow or solid. So the electric field isn't just 0 in the empty space. The electric field is 0 inside the conductor, and it's only points outside of this charged conducting sphere that there's any non-zero value to the electric field. So one of the key features of conductors that reach electrostatic equilibrium is that the electric field at points inside is 0. Now here's a different case. If we take a wire connected to the positive terminal of the battery and connect that to the light bulb and a negative terminal, so we complete the electric circuit, then charged particles start to flow through the wires. Now this is the positive and negative, or the high potential and low potential. The charge does not come from the battery. The charges that move through the circuit, they're already free electrons everywhere in the connecting wires. There are ions in the battery that represent charges that can flow. There are free electrons in the metal posts that support the filament, and there are free electrons in the filament as well. So the charge doesn't come from the battery. The charges are everywhere. The battery is just a source of a potential difference, and if all these charges were positive, then this charge would want to move this way, away from the high potential side of the battery. That charge would want to move in this direction. This charge wants to move this way, this charge, and all the charges start to move. Now we'll see in the next video in our study of what we call drift speed that they actually move very slowly. The signal travels almost immediately once the circuit is complete, but the charges themselves drift really slowly. In most cases, if the conductor is made out of metal, then these charges are actually negative because they represent electrons, and so the direction is opposite. Electrons would be attracted to the positive terminal of the battery, repelled by the negative, and so when the circuit's complete, all the electrons in this picture would want to circulate in a counterclockwise direction. If we zoom, well, first of all, let's make a schematic diagram, then we'll zoom in on a segment of the wire. Our battery is the source of electric potential difference. The filament in the light bulb contains the majority of the resistance in this electrical circuit, although the connecting wires themselves have some non-zero but usually negligible amount of resistance. So I want to zoom in on this segment of the wire. Actually, let's really zoom in on it a lot. So this end of the wire is at a high electric potential, and this end is at a low electric potential. Now what that does is it makes for an electric field inside the conductor. And electric field lines, as we know, point from high potential towards low potential. Let's draw those again. So that's really the role of the battery. What it does is it maintains a potential difference from one end of the wire to the other. And as long as the circuit remains connected, then that potential difference can't go to zero. There's always going to be high potential on this end of the wire. Maybe we call that point A. And then there's low potential at point B on this end of the wire. And if that potential difference remains, then the electric field never reaches zero. So that's a key distinction between our study of electrostatics and this study of electrical current. The only way you get an electrical current in a conductor is if the electric field is there to provide a force on the free charges. In the case of metal, those free charges are electrons, here symbolized as blue dots. Now, positive charges experience a force in the direction of the electric field. Because electrons are negatively charged, they experience a force opposite, and so they begin to drift toward the high potential side of the wire. In the next video lesson, we'll get into that drift velocity, and eventually we'll use this to define exactly what we mean by electric current, symbolized here by capital I. More to come.